This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 5, Lesson 5, Vibrating Systems, Part 1, Free Vibration. The springs we just sized store energy. Hang a mass on one, pull it down, and let go, and it oscillates at a single natural frequency. This lesson builds that natural frequency for a translating mass and for a torsional rod, adds damping, and shows how to collapse a real beam or shaft into one equivalent spring and mass. Forced response and isolation, wait for Lesson 6. Concept 1. The natural frequency. Sum the forces on a mass hanging from a spring. The weight exactly cancels the static stretch, and what's left is a clean oscillator. Its natural frequency is the square root of stiffness over mass in radians per second. There's a second root, because the weight equals the spring rate times the static deflection. The natural frequency is also the square root of gravity over that static sag. The same identity, handy when all you know is how far the spring drooped. Divide by 2 pi for the cyclic frequency in hertz. Concept 2. Torsional free vibration. A disc on a twisting rod is the rotational copy of the spring mass. Torque for force, angle for displacement, mass moment of inertia for mass. Its natural frequency is the square root of torsional stiffness over inertia. For a solid round rod, the torsional stiffness is Gj over L, so the natural frequency becomes the square root of Gj over IL. Watch the two look-alike symbols. J is the polar moment of the rod's cross-section. I is the mass moment of inertia of the disc. Concept 3. Damping. A real system bleeds energy through a viscous damper. Compare its damping constant to the critical value that would just kill the oscillation, and their ratio is the damping ratio zeta. Below 1, the system still rings but a touch slower. The damped frequency is the natural frequency times the square root of 1 minus zeta squared. To find zeta from a test, take the natural log of the ratio of 2 successive peaks, the logarithmic decrement, and back out zeta. One caution, this decrement delta is not the static deflection delta from 2 slides ago. Concept 4. Reducing a real element. A cantilever, a rod, a loaded beam. None look like a block on a coil, but the handbook tabulates their equivalent stiffness and equivalent mass, so you can still write the natural frequency as the square root of K equivalent over M equivalent. Notice the helical spring stiffness here is the very spring rate from Lesson 3, the same coil now driving a vibration. And the mass rows add a fraction of the beam's or spring's own weight to the mass it carries. Setup. Part A. A 5 kilogram mass on a 20,000 Newton per meter spring. After a tap, 2 successive peaks come in at 1 millimeter and 3/4 of a millimeter. We want the natural frequency, the cyclic frequency, the damping ratio, and the damped frequency. Part B. A disc on a solid steel shaft. Given the disc's inertia and the shaft's diameter, length, and shear modulus, find the torsional natural frequency. Everything's in SI, so the frequencies come out in radians per second directly. Solve. Part A. The frequency. Square root of stiffness over mass gives about 63 radians per second. Divide by 2 pi, and that's roughly 10 hertz, a period near 1/10 of a second. The static deflection route agrees exactly. The weight sags the spring about 2.5 millimeters, and the square root of gravity over that sag returns the same 63, because it's the same ratio, written a different way. Solve. Part A. The damping. The natural log of the peak ratio, 1 over 3/4, is the logarithmic decrement, about 0.29. Invert the decrement relation and the damping ratio is about 0.05. For damping this light, decrement over 2 pi is an accurate shortcut. Feed it into the damped frequency formula and the frequency dips by only 0.1%. So damped and undamped are practically the same here. Damping matters far more near resonance, which is Lesson 6. Solve. Part B. The torsional frequency. The shaft's polar moment is pi times d to the 4th power divided by 32. Multiply by the shear modulus and divide by the length for a torsional stiffness near 2,500 Newton meters per radian. Divide that by the disc's inertia, take the square root, and the torsional natural frequency is about 160 radians per second. It's the same square root of stiffness over inertia machine. Gj over L just plays the part of the spring rate. Traps. 5 ways this bites. 1. Keep the radian per second natural frequency and the hertz cyclic frequency straight. They differ by 2 pi. 2. Use consistent SI units, or the frequency is off by orders of magnitude. 3. In the torsional case, the polar area moment J and the disk's mass moment of inertia I are different things. 4. The logarithmic decrement is the log of the ratio of successive peaks, not their difference, and it isn't the static deflection. 5. When a static sag is given, the gravity over delta shortcut is the fastest route to the natural frequency. Quick recall. Free vibration is one idea in 3 forms. The natural frequency is the square root of stiffness over inertia. Translating, that's K over M, or gravity over the static sag. Twisting, it's the torsional stiffness Gj over L over the mass moment of inertia. Reduce any real element to an equivalent stiffness and mass, and the same square root applies. Damping, the critical constant, the ratio zeta, the damped frequency, the log decrement, only trims that natural frequency. Golden rule, collapse to 1 stiffness and 1 inertia, then take the root. Next up, Topic 6, Vibrating Systems 2. We now know the frequency at which a system wants to ring. The danger is driving it there on purpose. Lesson 6 builds the forced response, the magnification factor that makes amplitude explode at resonance, transmissibility, and how a soft mount isolates a machine from the floor beneath it. Everything's at peprepengine.com. Cheat sheet, work solution, and a quiz attached here. If the course helps, subscribe.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.